All right, we are going to be starting now. So, first of all, thank you everybody for coming today, choosing to spend your evening talking about artificial intelligence with us. My name is Jaime Sevilla. I do some research on applied computer vision. I'm also a deep learning engineer at Explore.ai, and I also volunteer as director of strategy for EA Spain, who is hosting this event today. Aside from you, I also want to thank our organizing team, with all the people who have helped putting up posters, all the people who have helped up with the outreach, and the people who are down there like guiding people to come here. Thank you, everybody. You deserve a round of applause right now. All right, so this is a talk about artificial intelligence. What are we going to be talking about? It so happens that many important organizations and companies today are devoting significant resources to researching problems associated with the design of advanced artificial intelligence systems. Today, I want to shed some light of why names like DeepMind, why names like OpenAI have created their own safety teams and are right now very concerned with some of the problems we will be exposing today. So, a few notes about interaction. We are a lot of people, but I would like to keep this dynamic. So I came up with this idea, and I hope you will enjoy it. In front of you, you have a sheet of paper. In this sheet of paper, there are some questions related to artificial intelligence. I'm going to ask you to please fill out the part that corresponds to before the talk. And then, after the talk is done, I will ask you to fill out the part that it's after the talk, and that will give me a measure of how your beliefs have changed during the talk. On the other side of the sheet, you have some space for notes. As I go along in the presentation, you are invited to note down your thoughts, your comments, your suggestions on this part of the sheet. All right? Is everything clear? Yes. OK, awesome. Thank you. So I'm going to give you now 1 minute so you can answer the questions that are in the front part of the handout, the ones that correspond to before the talk. You're asked to give probability estimates. If you're right now at the point where you're not comfortable putting numbers on those things, it is OK if you use the words that are indicated here. Do not obsess too much about it. Just give a quick impression. All right, was that enough time? Is everybody done? OK, I'm going to take it as that was enough time. So now, you can turn around the sheets. And here you have like an outline of what this talk is going to be like. This talk is split into 4 parts. First, we're going to be talking about generalization. OK, backing up 1 minute. This talk is not going to be about answers. That's something I want to have like very clear from the beginning. This talk is going to be about questions. I'm going to pose to you questions. I'm going to present you with some evidence which I think is suggestive. but I want you to draw out your own conclusions. Okay? So I want you guys to be in a mind frame right now where you are actively engaging with what I'm saying rather than just accepting it. That's not useful for me. I want you guys to think about these issues. All right? So now we're talking about why people are working today on problems of safety related to artificial general intelligence, to highly advanced artificial intelligence systems. I think that in order to understand why this is important, we first need to ask the questions. What will be machines capable of in the future? And that is the to ask ourselves, how good will these machines be compared to us in doing all those tasks? And that is the question of performance. Afterwards, we will look into, okay, what are the technical challenges that will prevent advanced artificial intelligence systems from being completely aligned with our interests? And that is the alignment question. And lastly, we are going to be talking a bit about what the people working today are working on and why they think that it is actually possible to work today in a problem that it's not going to happen until many years from now, possibly. Is everything clear to everybody? All right, awesome. So, generalization. What will machines be capable of in the future? We can imagine two very different futures. One in which we are developing artificial intelligence systems in which each of them is like really good at doing one thing, but only that thing. That is kind of like the reality we live in today. Like in your phone, you probably have lots of applications that are like really specialized and are capable of doing like one very concrete task. Today we have machines that are capable of playing chess, of playing Go. But you task them with if you pick one of those machines and you task them with climbing a mountain, it will not work. It will not do anything. However, there is an example of a physical system that exhibits what I call general intelligence in the world. As a system that is capable of performing not one specialized task, but many tasks, from building rockets to programming to giving talks. And of course, I'm talking about we're going to be examining 3 cases on progress on artificial intelligence, and we're going to be thinking whether we are going towards the world in which things are more specialized, or whether we're going to a world where things are more general, where the same artificial intelligence system will be capable of performing many tasks, as many as a human, perhaps. So we're going to start with computer vision, then we're going to move to games, and then we're going to talk about natural language processing. Computer vision. All right. How many people recognize this image? Nobody. That's great. So this is Shift. This is an object detection pipeline. It's composed of many modules. Like what you input here is an image. What comes out of the other way, it's a bounding box in an image telling you that, for example, here there is a title. All right? Does that make sense? As you can see, Shift was made in 2004. It's still being used today in industry. It is a really potent framework. It has many modules. It has one big problem too, which is that it is only able to recognize images as they are, but it's not really good at generalizing. I could plausibly use Shift to find out whether one particular cat matches one of my known breeds of cats that I have in my database of possible cats. But if it finds an image in which there is a breed of cat which is not in my database here, it will fail. It will not be able to identify it will not be able to tell that there is a cat in the image, even if it has seen like thousands of cats before, so to speak. This is not a learning system, but even if I have thousands of cats in my database, it will not be able to generalize the concept of cat. Whereas, like any human child could be able, after looking at 10 different cats, to be able to tell that, okay, this one is not a breed I have seen before, but it's still a cat. Okay, now fast forward to 2016. We get YOLO. How many people have seen this image? Somebody. Okay, that's great. So YOLO, you only look once, is also an object detection framework. It looks far more complicated than SIFT, but that is an illusion because all this thing is comparable to only one of the boxes that we have here. Okay? YOLO is not as constrained as SIFT. It is capable of performing many more tasks using far fewer modules. This one will be able to tell whether, if something is a cat, even if it hasn't seen that particular breed of cat before. Some qubits. Okay, next one, gaming. How many people have heard about AlphaGo and Lizzie Doll? Awesome, many people, right? So in 2016, we had an epic match in which Lizzie Doll, a professional Go player, played against AlphaGo, an artificial intelligence system designed by DeepMind. And AlphaGo pretty much kicked his ass. It won 4 out of 5 games, all right? How Alpha worked is that it had like 3 different components here that allowed him to perform some really nifty tricks in order to play Go really, really well. This was like really unexpected. People the year before, experts in artificial intelligence, were saying we're not going to solve the problem of beating a professional Go player in at least 20 years. And yet here we are. Fast forward 1 year. AlphaGo 0. AlphaGo, it was trained using data from actual matches between humans. AlphaGo 0 was not. It was trained using entirely self-play. Essentially, it was initialized randomly, and it played against itself until it got like really good. We also noticed that AlphaGo 0 has fewer modules than AlphaGo. And how does it compare? Well, it's actually much better than AlphaGo. Even while AlphaGo was something of a level comparable to a human player, as we will see later, AlphaGo 0 is way above human players. Like, I do not expect right now to be a human being alive who will be able to beat the latest version of AlphaGo 0. What is more surprising is that this framework, after appropriate training, also works for chess and shogi, which is a kind of Chinese chess, for the people who don't know. Okay, so I think this is surprising, right? Like, we're going from more modules to less modules that are capable of doing more things. Okay, another example, language processing. Language processing, how it was done classically, was using context-free grammars. Maybe you recall from school where the teacher would put you like a sentence and you had to split it into verbs, nouns, and group them. Essentially, that's how we did language understanding in the last century. This had a huge problem, which is that for each kind of phrase that you wanted to understand, you needed to build a new system with rules specific for those kinds of sentences. So sentences that, so if you build a machine that was able to to correctly process sentences in active voice, it would not necessarily be able automatically from processing things in passive voice, so to speak. You will need to like rewrite the entire system and incorporate rules for that. Fast forward to the future. In 1997, it was proposed the long short-term memory cells. They were not really used until 2010, but Right now, LSTMs and more generally what is known as recurrent neural networks are the state of the art in text processing. They are far more general than context-free grammars. And the same system, after going through an appropriate time of retraining, is able to process very different kinds of text. And of course, we cannot mention language processing today without making a mention to GPT-2. How many people have heard about this? All right, many people, really well. OK, so GPT-2. OpenAI is an it's a non-profit which is committed towards democratizing AI and making sure that AI is beneficially aligned with the interests of humanity, so to speak. They say it better, but they trained a system which is based on what are called transformer models, which are an alternative to RNNs. It's a thing that we had from a long time before, but they trained it on on text prediction. They essentially fed the system all of Reddit, and they built a system that was able to act as the predictor you may have in your phone, where when you're writing, it takes as an input what you have written so far, and it tells what is the most likely word that will come next. Okay, that's quite impressive on its own. It's working really well across many types of texts. But what is even more impressive is that without further retraining, GPT-2 did not only perform well in this task, but it also performed super well in many, many tasks. For example, it was able to get a 70% accuracy result in the Winograd schema challenge, which is a sort of cognitive test of sorts. It was also really good in text compression, which is something that I found interesting. You could use GPT-2 as to zip your files, as a lossy zip, but again, what I want to bring attention towards right here is that we have this simple concept, which are transformers, this system which has only one model, and it's really good at a huge array of tasks. Okay? So this is all for generalization. I think that what we have seen is suggestive that there is a clear trend towards systems that have less models but are capable of doing more things. Now the question is, exactly how fast is this progressing? And I think that the honest answer is we don't know. Experts disagree on when we are going to reach, if ever, human-level artificial intelligence, which, as you have in your sheets, is the level of intelligence that will be required. Well, it will be like a system capable of essentially performing any job a human can do today. Okay? So we're very confused about this, and we should have epistemic humility and say, okay, maybe there is a significant chance that in the next 70 years we will have machines that are capable of matching humans in terms of generality. The next question we may ask ourselves is, should we expect these machines to be much better at what we do than we? Of performance. So let's go into it. Okay. So performance. I think it's very useful when we think of performance to think in terms of sigmoids. This is a sigmoid. Essentially, when you start working very rapid improvements, but then it becomes increasingly harder to get better. Okay. This is a complete oversimplification, but I find that it's a useful frame to think, and it's what we are going to be using now to think about performance. The question that is natural to ask after we have contemplated the possibility of creating artificial general intelligence, human-level artificial intelligence, is, okay, we have humans, right? Humans seem to have this general capability of doing general tasks, all right? And like, we do not really know if the ability of humans to perform really well is like here, and there's like much room for growth, or whether we are already like near the top, right? And like whether our level of intelligence is already like so good, will be able to surpass us in a very long time. Now, let's look at two cases. Again, we're going to go with computer vision and games. In computer vision, there is the ImageNet challenge. How many people have heard about that? ImageNet. Fewer people, but some. Okay. So ImageNet is an visual processing challenge. It has many associated challenges, but essentially it's like a very big database of images that it is used as a benchmark for computer vision systems. All right. So if you want to know how good is your computer vision system, one thing you could do is you could test your system against this benchmark and compare it to other systems. And like here's a progression of top 5 error on ImageNet. Okay, this is like one particular challenge within ImageNet. It's about it's about classification. I show you an image, and you have to tell me what's in there, whether there is a cat, whether there is a horse. All right. Top 5 error means that I'm going to be like I'm not only going to ask the system for the best guess, but I'm going to allow them to write down like the 5 best guesses. And if any of those 5 best guesses is actually what's in the photo, then that example is correct. And like the question is here, how many images do the systems get correct? Like in 2010, 2011, the error rate was around 28%. Then it went down to 23%, and then something happened. We started getting like really low error rates with the introduction of deep learning techniques, such as what we saw before. It's a deep learning technique. It comes in 2016, so those are earlier deep learning techniques. If you want names, BGG16, AlexNet, that kind of stuff. And between 2014 and 2015, we got to human level of accuracy. This is what a human, what the top 5 error a human will get if it was asked to perform the same task of classification as an artificial intelligence system. All right, so what we saw is that in a very short time, like the artificial intelligence systems went from being like really bad at computer vision to being like comparable to human level, and they're actually now surpass human level, although those results are a bit unclear whether they actually generalize well to other image recognition tasks, but hey, it seems like they're getting better. Even then, I would expect humans to be close to called like top performance, right? Like for any tasks, there are like mathematical limits on how well you can perform. Like if I show you an image of a cat, but it's like really blurred and noisy, if you fail at classifying that, it's not because you're a bad classifier, it's because I am an asshole. So this is an example of what I say it's a natural task, which is a task that humans were actually, like to some degree, optimized to perform, which is recognizing visual patterns. That seems something that evolution will want to grant us if we want to live longer. Now, game playing. What happened in game playing? In 2014, the top performing system was Crazy Stone. It had an ELO rating. ELO rating is like how good is this program at playing Go, okay? Of around 2,000. We can see that today top Go players have ELOs of around 3,600. So this was significantly below the level of a professional. Then AlphaGo came along, and in its two first generations, AlphaGo Fun and AlphaGo Lee, it got to match human level performance. This is the one that was pit against Lee Sedol that we saw earlier. And now, it doesn't stop there. As I told you before, like the AlphaGo team kept improving their systems. And they get to 5,000 ELO with AlphaGo 0, which is vastly superhuman performance. This is a case of a class of tasks which doesn't feel natural to me. A class of tasks that requires abstract reasoning and for which evolution has not prepared us. So I think that we should not be surprised to see that artificial intelligence systems quickly went from subhuman to superhuman. Does that make sense? Okay, so everything together again. Like in the beginning, we were contemplating the possibility of human machines that possessed general intelligence, that were able to perform a very wide array of tasks. Now we're contemplating the possibility of artificial time from subhuman performance in a task to superhuman performance in a task. And this can sound like really cool, right? Like, come on, we are maybe going to get like very general artificial intelligence, which are going to be like really, really good. Imagine the possibilities. With artificial intelligence, you could solve cancer. You could end war. You could do pretty much anything that requires intelligence. There are many things that you can do with a sufficiently powerful artificial general intelligence. But not everything is easy. We have reasons to suspect that there are some technical challenges associated with the development of highly advanced AI systems. And it is important that we reflect on what those challenges are, which is what we're going to be talking about right now in the alignment section. So, alignment. For AI alignment, I'm going to be talking about the problem of programming an artificial intelligence in such a way that it is capable of, that it is going to do what its operator expects it to do. Okay? I'm going to be talking about three reasons to think that this is actually like a serious technical challenge, and point at some examples. All right? So we're going to be talking about orthogonality, we're going to be talking about convergence, we're going to be talking about fragility. This part is a bit more abstract, but I hope that you all guys are smart fellows and you will be able to follow. So, orthogonality. Okay, so right now we have like a very general framework of artificial intelligence, which is called reinforcement learning. In reinforcement learning, what you do is instead of programming a machine with a specific set of tasks of what to do, you give it a reward function, which essentially is going to be telling the machine like when it's doing something good and when it's doing something bad. So, equipped with this framework, you may want to do things like, for example, training a boat to go around in a circle in a predefined circuit. And like, what kind of reward can you give the artificial intelligence so that it learns to drive the boat well? It's like, okay, so in this game environment, like I'm going to say that every time the boat goes around, it's going to get like 1 point, all right? And also in the track, there are like some boosts, some collectibles, some coins, whatever you want, like are also good things that I want the boat to collect. So that give points to the artificial intelligence for collecting those items. Okay? Then what happens? This happens. Sorry. The machine quickly learns that going around the track is not efficient to get as many points as possible. Instead, it finds like a loop that it can do so that it is continuously collecting the items in the track. What this example is pointing towards is that specifying what we want is really hard. The machines are going to do exactly what we tell them to do and not what its operator intended. I like this. The problem with artificial general intelligence, the challenges associated with the alignment of highly advanced artificial intelligence is not a problem of a spooky consciousness, as Stuart Russell, like from the University of Berkeley, likes to say. It's rather a problem. It's rather a problem of the machine is going to do exactly what you tell them to. It's more of a. It's like the genie problem, right? Like, you know, this history, the stories where there's like a lamp and a genie, and you ask them for wishes, and the genie gives you exactly what you ask for instead of what you want. This is a useful way of thinking of what is going to happen with, what may happen with highly advanced artificial general systems. This brings us to the orthogonality thesis, which is the idea that no matter your goal, it doesn't like, your intelligence is not automatically correlated with goals. Like getting more intelligent is not going to automatically confer you like a moral sense, an ethical sense, and then you're going to pursue beneficial goals for humanity. You may have a goal that it's like very bonkers from a human perspective, be it really, really intelligent, very efficient at achieving it, and engage in behavior like the boat we saw earlier. Okay, so now we may ask, okay, so we may have some problems specifying how a boat is going to move, how an artificial general intelligence is going to, how to specify what we want it to pursue. But I mean, come on, the video before was funny, right? It was funny. It doesn't seem like that much of an issue if an artificial intelligence system like makes it's mistakenly programmed with a reward function, or like I don't want to talk about reward functions because I don't know what artificial general intelligence will be like. It might be a reinforcement learning system. But what I want to point towards is like if they have like an absurd task, if they're programmed with a task that does not represent what the operator wants, and they just make like a funny mistake and we all laugh and disconnect it and reprogram it again, like that would be great. That would be a good case for, okay, maybe we don't have to worry about this problem now, but let's just worry about that later when we actually have like highly advanced artificial intelligence systems with which we can tinker and that we can try our solutions on. But here comes convergence. Who here has heard before about the term instrumental goal? Some people. Okay, what is an instrumental goal? An instrumental goal is a goal such that for a wide array of end goals that you may have, achieving that goal is going to get you closer to it. So like one example in human society is money. Money, grosso modo, it's good. It doesn't matter what you want. It doesn't matter if you want to buy a Ferrari. It doesn't matter if you want to like help people in Africa. If you have more money, you have a higher capability of doing so. So money is an example of an instrumental goal. Now what we may ask ourselves is like, what instrumental goals could sufficiently advanced artificial intelligence pursue? And there are a few. And between them, the most important one is like, well, an artificial intelligence system would want to protect itself, and it would want to protect its specification of whatever their goals are. Because even if it's like very obsessed with like computing digits of pi, and we find that silly, the artificial intelligence won't. It's just like a decision-making machine. It's going to pursue that task relentlessly. And if it has a sufficiently advanced capacity of reasoning, then it's going to conclude that if I let the operator reprogram me again, I'm not going to be able to efficiently pursue my mindless task of computing digits of pi. So the artificial intelligence is going to be incentivized to not cooperate with us. Like this can be this can be an issue if the artificial intelligence has ways of preventing us from modifying it, or if it's like implemented in like highly sensitive systems. right? Okay, so we have learned that machines are not going to be aligned by default with our interests, and that in fact it may be really hard to test this out in the wild. So we have to get it right the first time, or we have to think about ways of like installing corrigibility mechanisms in the artificial intelligence, so that even if it fails, it will still be cooperative and help us align that, and not tell us but it turns out, like, is this difficult? Is it difficult to create, like, imagine we create an artificial general intelligence. Will it be difficult to specify what exactly what human wants? If we put like a super elite team of engineers project style, will they be able to come up in a year with like a reasonable solution to how to encode what humans value in a machine? And I think that the problem is like really, 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 really hard. And we may look at a suggestive example. This is a bit detached, but it's just, I think it's relevant. The example I want to bring is adversarial examples. All right, so this is from computer vision. When you have a classifier, like you enter to the classifier system an image, and it tells you what it sees there. But it so happens that if you have access to that system, you can compute a matrix of noise, such as this one, so that moving this, like adding this noise to this image, could cause the classifier to misclassify the image. This is a problem of fragility. This is a problem of the goal that we instilled into the classifier system, which is defined via a cost function, did not capture sufficiently well what we cared about. So when it started working with objects that it had not seen before, it broke in an unexpected way. Like, I think this is also going to be the case with humans because of something that's called Goodhart's law. Goodhart's law, as Marilyn Stratham said very eloquently, can be stated as when a measure becomes a target, it ceases to be a good measure. What does he mean by this? This is the idea that when you want to like make your machine do something, like you want to find like a proxy that that somewhat measures what you want from it. Like, think again about the boat, right? We wanted the boat to go around in circles, following the track. So we came up with a good idea. Like, our proxy of how well the boat is doing is going to be its punctuation, and we're going to increase that punctuation every time the boat collects an item and every time it goes around in a circle. But Goodhart's law, when that measure became the target, it ceased to be like a good proxy. Like, if you gave me a human operator that was playing that video game, that the measure of its punctuation would be like a really good proxy of how well the operator is piloting the boat. But once we gave it to an artificial intelligence and asked to optimize for it, it ceased to be. We have reasons to suspect that for whatever sophisticated goals we may want to instill in artificial intelligence systems, coming up with good proxies that accurately capture all we want is going to be hard. Okay, so how is everything so far? How is everyone so far? This is like, I'm totally following, I'm very engaged, and this is like, I'm getting kinderboard, or I'm not following you at all. Okay, lots of energy, that's good. So, we have seen that in the near future, we may have very general highly advanced artificial intelligence systems that outperform humans in critical tasks. And we also have seen that the problem of aligning them is like really hard, and like specifying the goals that we want them to follow. This paints a bleak picture, and the next natural question to ask ourselves is there something we can do? Like we have seen before that it is not good enough to just wait until we have highly advanced artificial intelligence systems, because those systems, because of instrumental convergence, could be incentivized to like not cooperate with us and not let us perform useful tests on them. So is there something we can do today when we don't even have access to such systems? And I think yes. And the reason why I believe that the answer is yes is because there are some suggestive historical cases of people working like very far in advance of like implementation, doing theoretical work, and getting like still like really, really good results. One such example is in chess. In 1950, this is early, Claude Shannon wrote a paper called Programming a Computer for Playing Chess, in which it described a theoretical algorithm called Minimax. How many people have heard about Minimax? Yes, yes, computer engineering pride, yes. Okay, so it described the Minimax algorithm that will allow a computer to play chess against a human. This algorithm was, for those days, completely impractical. It required like too much computation. It required resources that were not available at the time. It requires like computers that you can actually like program and debug efficiently. But almost 50 years later, in 1997, IBM designed the Deep Blue system and its successor, the Deeper Blue system, that played against Garry Kasparov in an epic match and won. I think that this example illustrates very well that you can do useful theoretical work in advance of artificial intelligence and the implementation of artificial intelligence. Other suggestive examples are, for example, Turing's works on computation that eventually led to the construction of computers. So let us see what people are working in today very briefly. Those are like 3 research agendas from 3 organizations that are concerned with the alignment of highly advanced artificial intelligence systems. The first one is Concrete Problems in AI Safety by OpenAI, in which it describes like some concrete problems that may arise from using advanced systems that are broadly similar to the systems we have today. MIRI is doing some more abstract work. MIRI is short for the Machine Intelligence Research Institute in San Francisco. They are trying to answer the question of what will a superintelligence do, even treating the superintelligence as if it was like a black box, really good at optimizing things. And lastly, we have AI Governance, a research agenda, written by Alan Dafoe from the Future of Humanity Institute. They are doing really awesome work on AI governance, because even if we get those technical challenges right, we still have to convince people to use the solutions that these people come up with. So thinking about how can we do that, and also like reflecting about the big strategic picture of AI development is really important. So if you're interested in those things, I want to encourage you to look up these research agendas and see for yourself what people are working on right now. And other things you can do is, for example, this Friday, people from here, Pablo Moreno, is leading the MIRI X Madrid. Although I think it will be on Wednesday. Okay, it will be on Wednesday?
Yeah.
Okay, so it will be next week on Wednesday. We will have meet X Madrid, where we will be discussing this paper, which is important to understand some of the work that these people are doing. You can talk to us if you're interested. Other things you can do is the Machine Intelligence Research Institute and CIFAR are organizing a Risk for Computer Scientists workshops. Those are 4-day workshops in San Francisco. They offer them free of charge to people who have studied computer science, computer engineering, and are interested in learning more about the issues associated to AI safety. So I recommend you check it out. And this is a bit higher level. The Midsummer Fellow Programs is a research program that will runs every summer for 3 weeks. And they are looking for people with a technical background who want to specialize in AI safety and try to make progress on these issues. And that's the talk. Thank you so much for listening. So now we're going to move to Q&A. How is time? 50 minutes. This is good. This is really good. So for Q&A, in your sheets, there is a code, and there is an address, which is slido.com. So if you have a mobile, and I hope you do, you can log into that Wi-Fi, and you can enter into slido.com, enter the code A682, and you can write down your questions and upvote the questions of other people. And in 2 minutes, we will be answering the questions that get the most upvotes. How exciting. All right, so I'm going to start answering questions. You can still write, and you can still vote. OK? So is it really OK to generalize so much from recent progress in deep learning as to how the progress curves of general intelligence will look like? The answer is no. I want to add some nuance here. I think that predicting the future is really hard. Like 1 year before Enrico Fermi invented the nuclear bomb, he stated very assertively that the nuclear fission was 40 years away. When you ask experts on artificial intelligence questions such as the ones that you have in your sheets, they disagree widely with each other. And this boils down in the end to the world is chaotic and unpredictable, and we don't know what is going to happen. I think it will be very audacious of us to assign a very low probability of the things that we have been discussing in the talk. But I see many people who are, yeah. I think that it's an outside view of the problem, and accept that forecasting is really hard. You cannot give precise answers. OK. Archive. Can we talk more about the tendency of programs to avoid being reprogrammed? Right. So I think this is quite natural. Like, if you could push a button that will change your goals to just lying down in bed all day, could you do that? And I want to think that the answer will be no, that you actually have like some goals that refer to external world, and you want to pursue them actively instead of getting orgasms every time you sit down on the couch. I think that this is like, I'm very loosely speaking, but I think that the case for the avoidance, like the case for defending yourself against reprogramming being something instrumentally convergent is like something that makes sense. It is something that if you are like smart enough to figure out like how to get to your smart enough at some point that you have to realize that if the things that motivate you change, the things that you're going to do are going to change as well, and you're going to be optimizing for different things, not the things you wanted in the first place. An interesting side effect of this is like artificial general intelligence could be incentivized to lie to us, because if we figure out while it is learning that actually their goals are not aligned with ours, we're going to shut it down and reprogram it. So an artificial general intelligence, then again, loosely speaking, is going to try to deceive its operators and try to make it seem as if it was actually optimizing for the thing we wanted. Because in that case, it will allow us it will be allowed to like keep going until it spirals out of control. Okay.
Can I present this?
No, you can write another question. Okay. If you have a sufficiently intelligent agent, why couldn't you ask it to do good? If it's intelligent, it will understand, no? I think the answer is no, in the sense of like, in order for you to be able to tell them to do good, like it will not be good enough to just tell them to be good. Like your systems, artificial intelligence systems, your intelligent systems are already programmed with some preconceived notions of what good means. So when you see good, like that actually translates to a complex thing in your brain that it's capable of making predictions about what is going to be good and what is going to be bad. If a human tells you, oh, don't litter, that is bad, like that has meaning for you. But that is not necessarily going to be the case for the AI. It's not going to have the same background knowledge that we have. We need to, and again, we need to get this right from the beginning. Like, you cannot naively expect to try to get a sufficiently advanced artificial intelligence so that it gets to the point where it can understand what good means, and then you tell them, do that. Like, that has to be in the system from the beginning. Kavitz, Paul Cristiano from OpenAI is working on a really interesting research agenda, which is called iterated amplification, in which, in my understanding of the question, of his approach, like he's actually trying to do that. Grossly, it's trying to get artificial intelligence to happen, the artificial general intelligence to happen in like progressive steps, so it can be, so it can use the artificial intelligence in each step to like better program the next one and better imbue it with a sense of the ethics that we have, that we want. That sounded really bad, but good enough. Hey, I want you. Okay, this is a really interesting question. What do you think about the ethic rules and policies that private and public organizations are publishing about the design of algorithms? So, we talked in this talk about GPT-2, which is a model that was created by OpenAI. OpenAI did something that is quite unprecedented in research, which is that it refrained from publishing the code of its fully trained network. And it did it saying that that network, that the system they had designed had some potential malicious applications that they wanted to discourage. I think that this is like a very bold move, and I also think that it's the correct one. They have set a precedent for thinking about what your system is going to be able to do before you release it to the wild. And I think that's a norm we want to encourage. Now, there's a different question of, do we want actual regulation here? And that is a really tricky question. If you are interested in that, I will refer you to the AI governance research agenda from Alan Dafoe of before and the work of FHI. I think they have like really interesting thoughts about that. Okay. How much computation was needed for alpha zero to surpass human performance? What are the chances this kind of approach will scale for AGI? Okay, for the first one, I cannot give you like exact details. What I can tell you is that AlphaZero, surprisingly, required far less computational requirements during training than its predecessor, AlphaGo. What are the chances that this kind of approach will scale for AGI? Then I am skeptical that you can just get a reinforcement learning system and just like train for a very long time and get artificial general intelligence. Then again, I was really skeptical that you could feed all of Reddit to a transformer and you will get a system that is capable of solving Winograd schemas. So the honest answer here is, I don't know. I think that we are still like 1 or 2 insets away from artificial general intelligence. I don't believe, like, if you start to think from an evolutionary perspective, whatever differences the brain of an ape and the brain of a human, whatever component allows you to build rockets and program and write poetry, it's not very different from what an ape has in its mind. So that leads me to think that, okay, maybe the model that gives you artificial general intelligence is not that complicated. But again, this is an educated guess, and predicting the future is hard. So honest answer, I don't know. Okay. What probabilities would you write on the sheet? I should have wrote them beforehand in case this question came up. This is a really smart question. So, assume for the purpose of this question, like maybe we can do it. We can do them together, right? Since you also have to put the after the talk one. Assume for the purpose of this question that human scientific activity continues without major negative disruption. How likely do you think then is the creation of human-level machine intelligence before 2070? That's 50 years from now. So I mostly do math to like clear up my own mind, but I don't think that just that there's like some math you can do to actually get this question right, obviously. Okay, so without having thinking much about it, I think that I would go for like 40% chance of human artificial general intelligence between 2070. Again, this is a very uneducated guess. I know people at DeepMind, for example, with whom I talked, and they tell me, oh, there's like a 50% chance that we will get to artificial general intelligence in 10 years. Okay, next one. Assume for the purpose of this question that human-level artificial intelligence will exist. How likely do you think is it that within 5 years thereafter, there will be machine intelligence that greatly surpasses the performance of any human in most professions. I'm going to go with 60%, but again, I feel actually like more uncalibrated about this question than the previous one. So take all my things with a grain of salt. Next one. Assume for the purpose of this question, hey, you are not cheating, right? You're not just copying my answers, right? I just realized that now. Do not do that. That is bad. You have to come up with your own conclusions. Assume for the purpose of these questions that such human-level machine intelligence will at a certain point exist. How likely it is that its overall impact on humanity will be positive in the long run. Well, here what comes to my mind is that I actually have like some uncertainty about moral theory, and I don't actually know what will end up like being a good result. But if we disambiguate this to what I think now that is most likely a good result, like, I don't know, we build a flourishing civilization and we get to the stars and we're able to live free of death and disease. This one's tricky. I'm going to be a coward and say 50%. No, I actually think it's more like 30%. That's a big update. You shouldn't trust people who update that quick, but okay. Last question. There is useful and meaningful work we can do today to increase the likelihood that highly advanced machine intelligence systems are beneficial for humanity. This depends on how you interpret the question. If your interpretation of the question is there useful work we can do today to understand better if this is a problem we can solve or not, then I think the answer is like almost certainly yes. I will assign 90% probability to it. But if we take this question as meaning after we think long enough for this problem and we start feeling less confused about it, will there be like actually like tractable paths that we can follow that will allow us to influence the impact of highly advanced artificial intelligence systems that may come 10 years from now, 70 years from now? I'm more skeptical there. I think I would go for, given our current level of understanding, towards 40%. It seems like a really hard problem. But again, close to 50% because nobody right now has like a really good grasp on whether this is something tractable on a technical level. I was thinking about technical work. Then I think that we can also we could also ask the question of what about policy work, and I think that in policy things are better. I think that there are like useful regulation that you can systems that you can promote, such what OpenAI did, that get us better chances of getting to beneficially aligned human level artificial intelligence. So for that, I will go for 70% for governance. Okay. How tired are you guys? How much do you guys want to go home and forget? Some people want. This is okay. This is a I want to keep going and with the questions. This is, I want to just end. Okay, maybe 2 more, and then it's over. Okay? How influential are organizations like MIDI or OpenAI? Do they have any soft power over people doing AI work? So, people in AI are quite divided about the question of a safety. There are people who think that there are people who really think that this is a problem that we should address. There are other people who think that this is not the priority. As to whether MIDI and OpenAI are influential, I think OpenAI is like really influential. I am really glad that they decided to not release the full GPT-2 model, because I think that that's going to send like a very good precedent going into the future. I think MIDI played a key pivotal role into bringing attention to the problem of AI alignment in the last decade. I do also believe that they do not have a comparative advantage in outreach, and they in fact have decided to stop publishing as often and focus more on trying to make headway into the technical issues rather than convince other people of working in it. Okay, the panda slide. Let's go back to it. It also says a giraffe, but there were no giraffes, I think. So this is the adversarial examples 1, right? So here what we have is we have a computer vision system which is trained for classification. So it takes as an input an image, and it is tasked to produce a label of what this image is. So like for example, here we have a happy, cute panda. And when we feed it into our neural network, it's going to spit out that, hey, this is a panda, which is a good prediction. But if we have access to the neural network in question, we can actually figure out like a matrix of noise, like some random distortion that you can, it's not random. This is very deliberate, very deliberately chosen. But you can like very slightly modify the pixel values of the input image in such a way that the system will output with a very high probability that what it is seeing is not a panda, but a gibbon. Okay, is it clear now? Okay, if somebody does not understand it yet, it can raise their hand and ask a question now. Okay, good. Those were the 2 ones, or this was the first one? Let's just answer the next one since it's easy. About performance, we always tend to compare machine performance with human one. Is there anything telling us that AI systems cannot improve indefinitely? And I say yes, those are the laws of physics. It doesn't matter how powerful your system are, there's like theoretical limits that it will not be able to surpass. Like there is, for example, a limit in computation. There is an amount of computation such that you cannot go faster than that, because otherwise you violate the laws of physics. And even though our understanding of the laws of physics may be flawed, I assign a very high probability that for those hard constraints, they actually hold. So I think that was everything. I'm sorry I cannot answer more questions, but I will be here around if you want to talk afterwards.